Mathematical formulation of a linear programming problem. Welcome, everyone. Before we dive into the new material, let's take a moment to reflect on what we covered in our previous lesson. We observed how real-world business decisions, like how much stock to order or how many workers to hire, are rarely unlimited. They are almost always restricted by certain constraints, such as budget or time. Now, as we move into today's topic, we face a new challenge. How do we take those messy, descriptive word problems and use them to make precise decisions? To use our mathematical tools effectively, we first need to translate those sentences into a structured mathematical model. This essential translation process is what we call mathematical formulation. Our ultimate goal with formulation is to represent the problem using clear, structured equations and inequalities. By doing this, we transform a complex story into a format where we can apply algebraic and graphical methods to pinpoint the exact, best possible outcome. Over the next few slides, I will show you the systematic steps required to achieve this. The process of formulation. Now that we understand that mathematical formulation is the essential bridge between a real-world word problem and a structured model, you might be wondering, how do I actually start? Well, it isn't just about guessing. To formulate a linear programming problem, or LPP, we follow a systematic, four-step process. In the next few slides, we are going to break down each of these 4 steps one by one, so you can learn how to approach any problem with confidence and precision. Step 1. Defining decision variables. Step 1 is defining our decision variables. When you are reading a word problem, your first task is to identify the specific quantities that the decision maker actually has control over. Think of these as the unknowns, the very things we are trying to figure out to solve the problem. To make these quantities easy to work with in our equations, we typically assign them algebraic variables, such as x and y. To make this concrete, let's look at a quick example. Imagine a company that produces 2 items, tables and chairs. In this scenario, the decision variables would be, let x represent the number of tables to be produced, and let y represent the number of chairs to be produced. Now that we understand that formulation is about translating words into math, let's dive into the very first step of this process. Once we have defined these variables, we can move on to the next step, which is ensuring our model stays grounded in reality. Step 2. Establishing non-negative constraints. Now that we have identified our decision variables, which, as we saw in the previous slide, are the unknown quantities like the number of tables or chairs, we need to apply a bit of common sense to our model. Think about real-world physical scenarios for a moment. In the real world, quantities like production numbers or labor hours simply cannot be negative. It is physically impossible to produce -5 tables or to employ -2 workers. Therefore, to ensure our mathematical model remains grounded in reality, we must explicitly state that our decision variables must be 0 or positive. In mathematical terms, we express this requirement using inequalities. We write that x is greater than or equal to 0, and y is greater than or equal to 0. As we move into the next step, we will see how these non-negative constraints work alongside our other limitations to define our boundaries. Step 3. Formulating linear constraints. Now that we have identified our decision variables, which, as we saw in the previous slide, are the quantities we can control, like the number of tables and chairs, we need to move to Step 3. Formulating the linear constraints. Think of constraints as the rules of the game. In any real-world business, you aren't free to produce infinite amounts of products. You are limited by certain restrictions. These limitations usually involve your available resources, such as your total budget, the amount of raw materials in your warehouse, the number of labor hours available in a week, or even the physical storage space in your factory. To translate these real-world limits into math, we use linear inequalities. When you are reading a word problem, you need to look for specific keywords to decide which symbol to use. If the problem says at most, or no more than, you will use the less than or equal to symbol. On the other hand, if the problem says at least or no less than, you will use the greater than or equal to symbol. Let's look at a concrete example to see how this works in practice. Suppose we are back to our production scenario. If each table requires 5 units of wood and each chair requires 1 unit of wood, and we know that our total supply of wood is limited to a maximum of 100 units, how do we write that? We take our decision variables from step 1, where x represents tables and y represents chairs, and multiply them by their respective resource usage. This gives us 5x plus y. Since we cannot exceed our total supply of 100, we write the constraint as 5x plus y is less than or equal to 100. This inequality mathematically represents our limit on raw materials. Step 4. Defining the objective function. Think of the objective function as the heart of the problem. It is the mathematical expression that represents exactly what we are trying to achieve. In most business scenarios, we are looking to do one of two things: either maximize something, like total profit or production efficiency, or minimize something, such as total cost, waste, or time spent. In our mathematical model, we represent this goal using a linear function, which we typically denote with the capital letter Z. To make this concrete, let's look at the example we started with involving tables and chairs. Suppose we know that the profit earned from selling one table is $250, and the profit from one chair is $75. Our goal is to find the total profit, which we will call Z. To calculate this, we multiply the profit of each item by the quantity produced, which we defined earlier as x for tables and y for chairs. Therefore, our objective function to maximize total profit Z is Z equals 250x plus 75y. Now that we have identified our unknowns and established our non-negative constraints, we move on to the final and most crucial part of the formulation. Step 4. Defining the objective function. In the next few slides, we are going to see how we pull all these individual pieces, the variables, the constraints, and this objective function, together to create one complete, comprehensive mathematical model. Comprehensive example: the furniture dealer. Now that we have understood the 4-step theory of formulation, let's put everything we've learned into practice with a comprehensive example. Please look at slide 7. Imagine we are acting as consultants for a furniture dealer. This dealer stocks 2 specific products, tables and chairs. To build our mathematical model, we need to carefully extract the data from this scenario. First, let's look at the dealer's limitations, or what we call our constraints. He is working with a total investment capital of $10,000, and he has a limited storage capacity of 60 square feet. Next, we look at the resource requirements for each item. For every table produced, it requires an investment of $500 and takes up 2 square feet of space. Similarly, each chair requires an investment of $100 and occupies 1 square foot of space. Finally, we have our goal, which will form our objective function. The dealer earns a profit of $250 on a table and $75 on a chair. Our ultimate objective here is to formulate a linear programming problem where the goal is to maximize the total profit. In the next few slides, we will walk through the 4 steps we just studied to translate this word problem into a structured mathematical model. Step-by-step formulation. Now that we have reviewed the scenario of our furniture dealer, let's apply the 4-step process we just learned to build our mathematical model from scratch. Starting with step 1, we need to define our decision variables. Remember, these are the unknown quantities that the dealer can actually control. In this specific case, the dealer needs to decide how many items to purchase for his shop. So, we will let X represent the number of tables the dealer decides to stock, and let Y represent the number of chairs the dealer decides to stock. Moving on to step 2, we must establish our non-negative constraints. As we discussed in our earlier slides, we have to ensure our model reflects reality. Since it is physically impossible to have a negative number of tables or chairs in a warehouse, we must explicitly state that X is greater than or equal to 0, and Y is also greater than or equal to 0. This ensures our solution stays within the first quadrant of our graph. Step-by-step formulation, continued. Now that we have identified our decision variables and established that they must be non-negative, let's move on to step 3, which is formulating our linear constraints. This is where we translate the physical limitations of our furniture dealer's business into mathematical inequalities. First, let's look at the investment constraint. From our previous slide, we know that each table costs $500 and each chair costs $100, and the dealer has a total budget of $10,000. To represent this, we say that 500x plus 100y must be less than or equal to 10,000. Now, to make our calculations much easier later on, we can simplify this inequality by dividing the entire expression by 100. This leaves us with a much cleaner version. 5x plus y is less than or equal to 100. Next, we have the storage constraint. We need to account for the physical space these items occupy. We know from the scenario that each table takes up 2 square feet and each chair takes up 1 square foot, and our total available space is 60 square feet. Therefore, we write this as 2x plus y is less than or equal to 60. By completing this step, we have successfully turned the dealer's real-world limitations into a set of mathematical boundaries. In the next slide, we will finalize our model by defining the ultimate goal, the objective function. Step-by-step formulation, continued. Now that we have identified our constraints in the previous step, we move to the final piece of the puzzle, step 4, which is defining the objective function. Remember, the objective function is simply the mathematical way of stating our main goal. In our furniture dealer scenario, the dealer's primary aim is to maximize the total profit, which we will represent with the variable z, since we know from our earlier data that the profit on one table is $250, and the profit on one chair is $75. We can write this as z equals 250x plus 75y. This brings us to the most important part of the lesson, the final mathematical model. This is the complete, structured summary of everything we have worked through. When you present a solution, you must present it as a single, cohesive unit. We start by stating our goal. Maximize z equals 250x plus 75y. Then, we follow this with the phrase subject to the constraints, which tells us that our profit is limited by the real-world boundaries we've identified. These boundaries are 5x plus y is less than or equal to 100, representing our simplified investment limit. 2x plus y is less than or equal to 60, representing our storage capacity. And finally, we must include our non-negative constraints. X is greater than or equal to 0, and y is greater than or equal to 0. By looking at this complete model, we now have a clear mathematical roadmap. In the next slide, we will discuss some common pitfalls to watch out for when setting up these models, so make sure you have a firm grasp on how these components fit together. Common mistakes to avoid. Now that we have seen how to successfully build a mathematical model using the furniture dealer example, I want to pause and discuss some common pitfalls. Even if you understand the steps, it is very easy to make small errors that can lead to an incorrect solution. First, let's talk about incorrect inequality signs. This is perhaps the most frequent mistake. Students often find themselves confused between the less than or equal to sign and the greater than or unequal to sign. To avoid this, always look for specific keywords in the word problem. If the problem mentions a maximum limit, a capacity, or says not more than, you must use the less than or equal to symbol. On the other hand, if the problem mentions a minimum requirement or says at least, you must use the greater than or equal to symbol. Getting this sign wrong completely changes the feasible region we are trying to find. Second, be careful about omitting non-negative constraints. You might think, well, of course, we can't produce a negative number of chairs, so why bother writing it down? However, in mathematics, you must explicitly state that x is greater than or equal to 0 and y is greater than or equal to 0. While it seems obvious in a real-world context, these constraints are mathematically essential because they restrict our solution to the first quadrant of the graph. Without them, your mathematical model is incomplete. Finally, watch out for mixing units. This is a subtle error that can ruin your calculations. Always ensure that all your units are consistent across the entire problem. For instance, if one constraint is expressed in hours and another is expressed in minutes, you must convert them so they are both in the same unit before you write your inequality. If you don't, your coefficients will be mathematically incorrect. Keep these 3 points in mind as we move toward our final summary of the lesson. Key takeaways. All right, we have reached the end of our lesson. Before you move on to practice problems, let's quickly recap the key takeaways from today's session to ensure you have a solid foundation. First, remember that formulation is the essential first step. It is the process of translating a descriptive word problem into a structured mathematical model that we can actually solve. Second, we have our decision variables, which we usually denote as x, and y. These represent the specific quantities that the decision maker can control, the unknowns we are trying to determine. Third, never forget the non-negative constraints. We must explicitly state that x and y are greater than or equal to 0. This is crucial because it ensures our mathematical solution is physically possible in the real world. After all, you can't produce a negative number of products. Fourth, we have our linear constraints. These are the inequalities that represent the limitations or restrictions of the problem, such as limited budget or available space, using symbols like less than or equal to or greater than or equal to. Finally, we have the objective function, represented by the letter z. This is the linear equation that defines our ultimate goal. Whether we are trying to maximize something, like profit, or minimize something, like cost. If you can master these 4 components, you will be well on your way to solving any linear programming problem. Great job today!